Hi guys, welcome back to the channel. In this lecture, we are going to find out the collapse load for this continuous beam in which the point load is acting on this AB portion, this 1.5 WC load on this BC portion, and this point load WC on CD portion. Okay, we need to calculate this collapse load value WC. Okay, WC we need to find what will be the collapse load for this continuous beam. Okay, and in this problem, one thing is different is that MP value is different. Okay, for AB portion MP is 600, for BC MP is 900, and for CD MP is 600. Okay, so area of cross section of this portion AB it will be less than the area of cross section of BC. Why? Because MP value is more over here, and we know that this plastic moment is basically the property of cross section. Okay, it depends upon the cross section. So the cross section area for this portion BC will be more as compared to AB and CD. Okay. Generally, if we want to have an economical design, we do these type of things. Okay, we vary the cross sections. Okay, so now one more thing is that we need to solve this problem by kinematic method, right? And the plastic hinge, whenever these two beams are meeting at a point, the plastic hinge will form in the weak member. Okay, the plastic hinge will form in weak member. Weak member means between these two members, between these two AB portion and BC portion, the plastic moment capacity of BC is more than AB. So plastic hinge will form just left of this support B. Okay, in this member. Okay, here also the plastic hinge will form just at the support, just right of the support C. Okay, so this is I meant by what is this is the meaning. This is the meaning of this thing, that plastic hinge will form in the weak member. Okay, because plastic moment capacity is less over there, right? So we have discussed this type of problem in static equilibrium method, where we came to conclusion that while discussing those problems in static equilibrium, we came to one conclusion that in the continuous beam there will be a partial collapse. Okay, there will be partial collapse of the structure. Partial collapse of the structure. Okay, what I meant by partial collapse means, what is the static indeterminacy of this beam? The static indeterminacy of this beam is equals to one reaction at this point, one reaction at this point, one reaction at this point, one reaction at this point. Okay, so total number of reactions are 4, equilibrium equations are 2, right? I am neglecting the horizontal reactions. So static indeterminacy is 2. So plastic hinge required for collapse will be 2 plus 1. Okay, so three plastic hinges are required for the complete collapse of this structure. Okay, but if you consider the partial collapse of the structure, it means that either the beam will collapse for this AB portion, or for this BC portion, and for this CD portion. Okay, if there is a partial collapse in AB, let us suppose if the collapse is taking place in AB. Okay, so how many plastic hinges are required? One plastic hinge will be required at this point, and one plastic hinge will be required at this point. So two plastic hinges are required. Two plastic hinges are required to collapse AB portion. Okay. So through this formula, the total hinges are required are 3. But if you want to have the partial collapse in the structure, the total hinges are required, with plastic hinges are required are 2. So this is the partial collapse of this structure. Okay. So in the continuous beam, we need to check different spans. Okay, first I will check this AB span, then this BC span, and then this CD span. Okay, I won't check for the complete collapse of the structure because that load will be more. Okay. So now let us come to this first span AB. Okay, for span AB, the plastic hinges will form under this point load and at this B support. Okay, so if you consider the plastic, this span, it is looking like this. So one plastic hinge will form under this point load, and one plastic hinge will form at this support, because moment is there. At this point there is no moment. Okay, so there is no plastic there is no plastic hinge over here. Okay, so when this beam will deflect during the collapse, it will deflect like this. This is the deflection during the collapse. Okay, that's why we are showing the straight line, right? So here, now we need to find the collapse load using the formula, using the kinematic method. Kinematic, or you can say that mechanism method. Okay. So in kinematic and mechanism method, we have one principle of virtual work, in which we studied that external work done plus internal work done is equals to 0. Okay. So here I can write external will be equals to minus of internal work done. Okay. Then we again modified this thing. So work external equals to mod of work internal. Okay. So now, why you are saying it's kinematic method? Because here we are giving one kinematic displacement which is delta. Okay. At this point, the rotation is, let us suppose theta. Here also the rotation will be theta, because this plastic hinge is forming at the center of this span. Okay. This angle will also be theta, alternate angles, this will be also theta. Okay. Now, what will be the external work done? External work done will be WC into delta. This W load is acting along this delta, so that's why it is positive. Okay, so this is W external. Okay, what will be the internal work done? Internal work done will be at this point, empty direction will be like this, and here the empty direction will be opposite to rotation. Okay, so internal work done I can write MP into theta minus MP into theta, again minus MP into theta, and here also it will be minus MP into theta. Okay. So we need to find the mod work internal. So this will be equals to 3 MP theta. Okay. Right. Okay guys, there should be no doubt in this. Okay, why we are taking negative? Because this MP and this theta directions are negative. That's why it is minus MP into theta. Okay, now the principle of work done, virtual work done, will say that this 3 MP theta will be equals to WC into delta. Okay, delta I can write, this is 4, this is 4. Through the properties of triangle, delta will be equals to 4 into theta. Okay, so this is 3 MP into theta equals to WC. WC we have to find, theta is 4 into theta. So theta will cancel out each other. MP value will be 600. Okay, the plastic hinge at this point will form in weak member, right? So this is 3 by 4 equals to WC. So if you calculate this value, this value WC comes out to be 450 kilonewton. Okay. So this is the first case we have discussed in which there is a partial collapse is happening. Okay, and we are taking this span AB. Okay, so when AB span will collapse, the plastic load required will be 450. Okay. Similarly, if CD load will collapse, if CD span will collapse, okay, then also the plastic load, then the plastic load is required. Again, it will be equals to minus 450 kilonewton. Why? Because this is symmetrical to this thing, right? Now let us consider the partial collapse of the collapse of this span BC. So again, if you are considering the collapse of this span BC, so this is BC span, and here this load 1.5 WC is acting. Okay, So now you can see that for the collapse of this span, this BC span, right? But you can say that the plastic hinges required will be at this point, and at this point. Okay. 3 plastic hinges is required for the collapse of this BC span. Okay. So now you can see that still here you can see that the three hinges are required basically to form the collapse. Okay. But in this end span only two hinges are required for the collapse. Okay. So during the collapse it will deform like this. This is the deflection during the collapse. Deflection during collapse, right? So this is a deflection during collapse. At this point, again, this will be MP. Okay. This is theta. This is again theta. This will be theta. This will be theta. Here, the direction of MP will be like this. Let us suppose this is MP1, because at this center the plastic moment capacity is 900, so it will be different than this MP. Here also this is MP1, and at this point this will be MP, because the plastic hinge will form in the weak member, that is CD. Okay. So now apply the principle of virtual work. Principle of virtual work. So if you apply the principle of virtual work, what is the external work done? So work done external will be equals to 1.5 WC into delta. So we are applying one kinematic displacement delta. That's why this method is called kinematic method. Okay. So 1.5 WC into delta. Right. So this will be equals to mod of internal, sorry. Why we are keeping this mod? We have already discussed. Okay. So this value will be equals to MP into theta, right? Minus MP1 into theta 1, again minus MP1 into theta 1 minus MP into theta. So this value will be 2 MP theta plus 2 MP1 theta. Okay. So this is equals to 1.5 WC into delta, right? So MP value we know, MP1 value we know, right? So this is theta common, 2 into 600 plus 2 into 900 equals to 1.5 WC. And what will be the value of delta? Delta will be 6 into theta. So theta will cancel out each other, right? So the value comes out to be 2 into 600 plus 2 into 900 divided by 1.5 by 6. So WC value comes out to be 333.333 kilonewton. Okay. So WC value, collapse load value when the collapse is taking place in span BC is 333.33 kilonewton. Okay. So we have studied that minimum of these three value will be our collapse load. Okay. So collapse load is basically that load which will make this beam collapse. Okay. So here this WC value will be, okay, here also this WC value is 333.33, okay, and 1.5 into 1.5, so this value is 500. Okay, so when you are applying this combination of load, there will be the collapse in this BC span. Okay, this AB span won't collapse, this AB and CD span won't collapse, but this BC span will collapse. Okay. Now let us check whether this is our true collapse load or not. We'll draw the bending moment diagram at the collapse and check whether this is our true collapse load or not. Right. Now Now for the bending moment at collapse, let us discuss two things. Okay, at this B point, there is a plastic moment. At this B point, there is a plastic moment of MP. Okay, direction we have already discussed. So I am drawing this plastic moment at the supports. Okay, here also this will be MP and this will be MP. Okay, so this is basically our reactant bending moments. Okay, because these are the reactants generated at the support. Okay, so these are our reactant bending moments. So if you draw the bending moment diagram of these reactants only, considering these reactants, okay, so it will look like this. Okay, this is MP, this will be MP, and this is hogging moments. Okay, this will produce hogging in the beam, so that's why they are negative, right? So what I did over here is that this thing we have already discussed in you can say that it's a static equilibrium method. So let us, if you draw the bending moment diagram of this bending moment diagram at the collapse, okay, so at this end we know that what are the bending moments. Okay, so these are basically the reactant bending moments. Okay, and if you draw the free bending moment diagram for this beam, considering at this point as a redundant, okay, free bending moment diagram due to redundant, at this point the bending moment for this spans, the bending moment diagram will look like this. Okay, and the value will be PL by 4. The maximum bending moment will be PL by 4. So this is again 333.33. This value is 500 PL by 4. Okay, that is what 8 divided by 4. This is 666.66, right? So this bending moment at this point, this will be 500 into 12 divided by 4, PL by 4. This value is 1500, and again this value will be same 66.66. Okay, so 333.33 into L, 8 divided by 4. Okay. So now this is our free bending moment diagram, and this is the bending moment diagram due to reactants. Okay, reactant means you can say that redundant also. Okay, so if you divide this span into three parts, what is a free body diagram? So here, let us suppose this is B. Here the bending moment is acting like this. Again, at this point the bending moment is acting like this. Similarly, at this point, for this span, the bending moment will look like this, and for this span, it will look like this. Okay. So if you draw the bending moment diagram, just considering the reactants, it will look like this, no? Okay. Here also this is MP. Here also this is MP. So the bending moment will be a constant line, right? Similarly, for this part, the bending moment will look like this. So if you combine all those things, the bending moment diagram due to reactants will look like this. Okay, but the load is also acting. So this is our positive bending moment, because this load are produced sagging. So if you overlap these things, these two bending moment diagrams, so it will look like this. Okay, so the bending moment diagram will look like this, right? So this value will be 900, 900. Okay, this is 600, 600. So 1500 minus 600 is 900. Okay, this scale should be a little bit more. Okay, the scale of this diagram. This is 600. Okay, here this will be negative, 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 and this negative portion, the hogging is taking place. Okay, so you can see that this is the bending moment diagram due to collapse. We just overlapped two bending moments, right? So you can see that the bending moment value is never crossing the MP value. Okay, so this is our true collapse load. Here you can see that the collapse is taking place in this member BC, because here the plastic moment is 900. Okay, which it will result into the plastic ink formation. Here also the plastic moment is coming out to be what you can say that 600, right? So the plastic ink will form at B, and at this point, under this point load, and this C point, right? So the collapse will take place in BC, and this yield condition is also satisfied. So this, what you can say that the WC 333.33 is our true collapse load. Okay, guys.